Okay, thank you very much for the invitation. It's nice to be here. So my talk is kind of a continuation of the talk of Dimitri. So in Dimitri's talk, it was our joint result from about 2 years ago. It was about kind of functions that are defined using Pfaffian function, this Chovansky's theory of phenomials. So I want to just kind of tell you why this is not enough, and why kind of the really interesting thing is to replace this by general foliations. And that's why you should be interested. So, okay, so let me just kind of explain why this Pila-Wilkie theorem is kind of became very fashionable and many people are using it. So there was a theorem of Pila and Wilkie. This was a kind of around 2006. And then very quickly people started finding many applications in the diophantine geometry for this result of Pila and Wilkie. So the first one was for this Manin-Mumford. Manin-Mumford. So this is the example that Dimitri gave. So, and this wasn't the first proof. So this is a proof of Manin-Mumford using Pila-Wilkie. This was done by Pila and Zannier. And this is basically the proof that Dimitri showed you for a baby version. But it was known before, for instance, by Renault. So the reason it kind of became very popular is that later people found proofs of many other conjectures in diophantine geometry where there are no other known proofs. So the first kind of big result was Andre Oort. So it was for modular curves. This is the first result for modular curves. This was done by Pila. Then there are many other kind of cases that people did, and then most general is for AG. So for the moduli space of abelian varieties of any genus, this is done by Zimmermann. So kind of all of these Andre Oort results, they are only known using this Pila-Wilkie theorem. So there are other proofs that are conditional on the Riemann hypothesis. But without the Riemann hypothesis, the only proof uses Pila-Wilkie. And then there are many other results by Masser and Zannier and their students that I will not have time to mention. But kind of there are many other diophantine applications where, again, Pila-Wilkie gives the only known proof. Okay, so that's why people became very interested in this theorem. Now, this particular application for Manin-Mumford, Manin-Mumford is a conjecture about semi-abelian varieties. So to study this, you need kind of Pila-Wilkie for abelian functions, for sets that are defined using abelian functions. And abelian functions actually are Pfaffian what Dimitri talked about. They satisfy these kinds of Pfaffian differential equations. So you can do this part using the techniques that Dimitri talked about. But if you want to study the Pila-Wilkie theorem for all of these other applications, it's not enough to look at abelian functions. What you need are modular functions, or period maps, or universal covers of Shimura varieties, theta functions in this case. So you need many different kinds of functions that don't seem to fall under this. They are not Pfaffian as far as we know. And if you could kind of improve the Pila-Wilkie theorem for such functions, you can hope to get a lot of information. So for example, you can hope for an effective solution of these conjectures. All of these conjectures say that some set of special points is finite. Like in Manin-Mumford, it was a set of torsion points on some curve. So here it says the set of CM points on a curve is finite. You could hope to actually compute this set. So in order to do that, you need a more effective form of this Pila-Wilkie theorem. But everything that Dimitri talked about will not help with that, because it's just the kind of functions that you need don't fall into that category. So I want to talk about more general kind of results for general foliations that does include all of these cases. OK, so I'll start with just my setup. OK. So I will consider a general foliation, and it will be on some ambient variety that I'll, just for this talk, I'll take to be c to the n. Okay, it doesn't really matter. So my ambient space will be c to the n, and I'll take a collection of vector fields, xc1 up to xcn. Oh, I'm sorry, this is big N, and c1 up to xc small n. They are polynomial vector fields. Defined over Q. Okay, so this Q could be replaced by a number field. It doesn't matter, but I do need it to be defined over a number field. And for simplicity, I will stick to Q in this talk. So, and I'll also assume that they generate a foliation. Okay, so I'll take F to be this foliation generated by Xc1 up to Xn. And let me assume, again, just for simplicity, that they commute. So Xi is 0. Okay, so I have a set of commuting vector fields, and they span some foliation. You could do it in invariant language without fixing the vector fields, but it just I need it for some normalizations. Okay, so now whenever I have a point P in M, there is a leaf of my foliation passing through this point that I will denote by LP. And I need one more. OK, so let me, for the whole talk, I'll fix one leaf. I'll fix L to be just the leaf passing through 0. Again, doesn't matter, but for simplicity. Now, on every leaf, you have a canonical set of coordinates given by these vector fields. Okay, just the flow of these vector fields defines you a coordinate on the leaf. Okay, so if I have this leaf L, then on it I have kind of this, this will be Xc1, this will be Xc2, then Xc3, etc. So I will always use, when I say Xc coordinates, I mean the coordinates given by the flow of these Xc vector fields. And I will denote by ball in the leaf L of radius r. This will be the ball of radius r. I mean, in these coordinates, in the Xc coordinates. Let me even take, let me even say just a BR, and it will be a ball in this L0. Okay, so I fixed a leaf, this L0, and in it I have balls that are just given by, if there are balls around the origin and with respect to this coordinate system. Okay, now I come to some non-trivial definition. Okay, so what I'm interested in, the first thing I'm interested in is kind of counting intersections between these leaves and varieties of complementary dimension. Okay, so just like in Dimitri's talk, we had something like a Bezout theorem. He said that when you have a function defined, when you have a set defined using Pfaffian functions, you can control the complexity. You can count the number of solutions like in the Bezout theorem. So I would like to have something similar in this more general context, where you just take a leaf of foliation, you intersect with some algebraic equations, and you want to know how many isolated solutions you can have. And unfortunately, we don't have a very good analog of this Pfaffian theory in this case, but I will give you some kind of partial analog. OK, so now let W in M be an algebraic subvariety. Let's say of codimension less than or equal to n. Okay. Then I define this sigma W. I call this the unlikely intersection locus of W. This will be the points P in M such that the dimension of W intersect the leaf at the point P is greater than what it should be. So it's greater than n minus the codimension of W. OK, so we are taking leaves of dimension m. It's an n-dimensional foliation. We are intersecting with something algebraic of a given codimension. So generically, it should intersect in this codimension, but it could happen that the leaf is contained in W or something. So I call this the locus of unlikely intersections. This is sigma W. So unlikely intersections. So this name is motivated by kind of an area in the Diophantine geometry called unlikely intersections. And in fact, many of these unlikely intersections that you get in the Diophantine geometry, there are special cases of this definition. So when you take the foliation to be, let's say, foliation by linear flows in an algebraic group, then these unlikely intersections will be exactly what is called unlikely intersection in tori in the Diophantine geometry. Or when you take the foliation to be a foliation connected to the modular structure on a modular curve, then these kind of unlikely intersections will be exactly the unlikely intersection with special subvarieties that you get in Andre-Ort. So it kind of generalizes many of these unlikely intersections that you get in the Diophantine geometry. And I claim that this is kind of relevant when you want to count the intersections between a leaf and an algebraic variety. So now let me give the first theorem. By the way, let me just, for technical reasons, I'll throw in here the singular part of f. Okay, so if f is singular, I always throw it. I always consider it kind of a part of this bad locus. And now I can state my theorem. So theorem 1. So suppose that now we are in the situation that the codimension of W is exactly n. Okay, so that means we have kind of leaves of dimension n. We have an algebraic variety of codimension n. We should expect them to meet at points. Now the theorem says that if you take this ball of radius 1 and intersect it with W, I take this set and I count the number of points. This will be less than or equal to some polynomial depending on the foliation in the following data. Delta of W, I'll define what this is, and the log distance inverse between our ball, B. Let me, instead of B1, I'll write just B. So this BR is the ball of radius R, and I'll say that B is just a ball of radius 1 to avoid writing 1 all the time. So I intersect my standard ball with W, and I claim the number of intersection points counted with multiplicity is polynomial in delta of W and the log distance to this unlikely intersection locus. Okay, and I should tell you what this delta of W is. So delta of W, this is the maximum of the degree of W and the logarithmic V height of W. Okay, so if you don't know logarithmic V height, you can think, for example, that W is defined over a number field by some explicit equations. And this will be roughly the number of bits that you need to encode all of these equations in a computer. So it's kind of the complexity of the coefficients of the equations of W. So what is very important here is that this is the logarithmic height, and this is the logarithmic distance. Okay, so kind of in the applications, the fact that you get a logarithmic height rather than the full height, and the logarithmic distance rather than the full distance, this is really the crucial point in this theorem. So I knew how to prove such a theorem already a few years ago, but there I got the distance and the height. And when you try to use this in the Diophantine applications, it's not strong enough. So kind of in the Diophantine geometry, you kind of expect things to depend on the degree and the logarithmic height. And you expect, when you have something like a Loashevich inequality, you expect to get the log of the distance. So this is kind of the right order of magnitude in this theorem that makes many applications work later. Yeah, I'm assuming it is defined. So I'm assuming it is defined, and I mean the constant here is kind of depending on the foliation. So in fact, I'm assuming that this ball is contained in some, let's say, in some fixed ball in the ambient space, and the constant depend on the size of this fixed ball in the ambient space. In fact, the dependence on all these constants is completely explicit, but just to make it simpler, I'm writing it in this way. But yes, I should assume that, I mean, this is really a ball. I mean, there is such a ball which is well defined. Okay, so this is the first theorem, and this is kind of a replacement for these results of Chovansky. So it means that you can count the number of intersections. You have to kind of stay away from this bad locus. So this is something that we have to pay. I don't think this is really essential. And I believe that such a result should be true without this term. But I don't know how to get rid of it. And I mean, it is kind of weak enough, because it is logarithmic, it is weak enough that in the applications, often it doesn't matter. But I mean, an ideal result would be just without this log distance, and maybe even without this height here. It's also plausible. I mean, this is what you get for Pfaffian functions. For Pfaffian functions, you get a bound that depends only on the degrees. OK, so this is one result. Then the other result that I want to talk about has to do with these Weierstrass polydisks that Dmitry defined. So Weierstrass polydisks. So Dmitry showed them, but I will not assume that you remember what he said. So basically, a Weierstrass polydisk means that we have a set. Let's say we have omega in C to the n, which is just a domain. And we have x in omega, which is analytic and pure dimension m. Then we say that a Weierstrass polydisk is something of the form delta z times delta w. So it's a product of two polydisks such that the dimension of delta z is equal to m, and delta z times the boundary of delta w does not intersect x. Okay, so that means we have this kind of picture that was in Dmitry's slides. So this is delta z, this is delta w, and x is somehow living here, something like this. So the branches of x cannot escape from the boundary of the fiber. So as you move in the base, you just get a collection of points, and they're moving in the fiber and can't escape. Okay, so this is something that we started using in order to study these rational points on analytic sets. So if you hope to do something like the Pila-Wilkie theorem, it would be very useful if we can also cover sets by these Weierstrass polydisks. So that is what my second result will be about. Okay. That's not perfect, this engine. Okay, never mind. Maybe I'll try it there. Okay. Okay, so the second theorem is kind of similar to the first theorem, but about covering by Weierstrass polydisks. So this is another theorem. It says that, so now I'll take a W which is of codimension less than or equal to n. Okay, and I will be interested in covering the intersection of my leaf with W by Weierstrass polydisk inside a leaf. And in fact, the theorem says that you can cover all of BL. So this B or BL, you can cover the ball, can be covered by so the same estimate, so by a polynomial number depending on the foliation in delta of W and this log distance inverse between the ball and sigma of W. So by this number of Weierstrass polydisks for the ball intersected with W. Okay, so inside the leaf, we are intersecting with W. We get some analytic set, and we will cover the whole ball by these polydisks that are Weierstrass polydisks for this analytic set. So it is kind of a generalization of the first theorem, and this is what we would like to use in order to count rational points, as it was in Dimitri's talk. So let me just recall how the proof went, how Dimitri's proof went. So what was the proof structure when we were trying to count rational points? So for this Wilkie conjecture. So in the Pfaffian case that Dimitri did, so Pfaffian case, Pfaff case, it was something like this. We had phenomial theory. So this is just known by Chovansky 40 years ago. And then this gave us something like theorem 1. I mean, it's the analog of theorem 1. And then from this theorem 1, we deduced theorem 2. Okay, so Dimitri showed you how using phenomial theory, once you know how to count intersections, it allows us to cover by Weierstrass polydisks. So we got from this theorem 2. And from this, we got kind of a Wilkie conjecture. So we got Wilkie. So when I started working on this problem with foliations, I mean, I expected the same kind of proof. I said I'll find some replacement for phenomial theory. I will prove something like theorem 1. Then using this theorem 1, I will get something about Weierstrass polydisks. And then once I know how to do that, I can do something about counting rational points. But in fact, it's not quite how it worked out. So for the general foliations, the proof looks quite different. So for the general foliations, the proof looks like this. We have theorem 1, and we have theorem 2, and they're actually proved by a kind of concurrent induction. Okay, so I prove theorem 1 in one dimension. I get it from it theorem 2 in the same dimension, but then I use theorem 2 to prove theorem 1 in the next dimension. Okay, so it's kind of here you just get theorem 1 by some completely different arguments from phenomial theory. But here, to get theorem 1, actually, it's helpful to have theorem 2 in the previous dimension. And then once you have both of them, then you can use this to get the Wilkie conjecture. Wilkie. So kind of the message is that even if you don't care about counting rational points, then, I mean, a priori, you don't care about these Weierstrass polydisks. But actually, I need them. I cannot prove theorem 1 by itself. I have to get theorem 2 as well. And these ideas that we used to get theorem 2 out of theorem 1, you need them in this general foliation situation. OK, so let me show you roughly how these two kind of steps of the reduction work. OK, so one step is going from theorem 1 to theorem 2. And this is quite similar to what Dimitri showed. So if you have theorem 1, it means you know how to count intersections. Now we want to do a covering by Weierstrass polydisks. This is roughly what was in Dimitri's talk, but slightly different. So what we're trying to do, so we try to find a Weierstrass polydisk. So it means delta z times the boundary of delta w intersected with x. So x here is the ball intersected with w. So we want to find such a thing. OK, and as Dimitri explained, it's kind of enough to find. So it is enough to find a ball such that the ball is disjoint from S1 times x. Okay, so if you can find a ball which is disjoint from the rotation of this x, then inside this ball, inside the rotation of this ball, you will find the Weierstrass polydisk. So this is what Dimitri showed. The problem is that this set is real analytic. And we have X, it's a complex analytic set, but now we rotate it by S1, so we get a real analytic set. And in the Pfaffian situation, it wasn't a problem. The Pfaffian methods are real to begin with, so we could kind of work with this set. Even though it's a real analytic set, we could work with it, and we use this Vitushkin formula, and everything works as Dmitry showed. But here it doesn't work. Kind of this set is not complex analytic, and I don't have any real analytic tools to use. I don't have this Pfaffian theory of Chovansky, which is real analytic. So I need to somehow study this using complex analytic methods. And the basic idea is to show that X can be covered by something like volume of X times 1 over epsilon to the dimension over R of X balls of radius epsilon. Okay, so this is what I want to show. I claim that this is true whenever you have a complex analytic set. Let's say you have a complex analytic set inside the unit ball. You want to cover it by epsilon balls, and you ask how many will I need. Now, if I don't need too many epsilon balls, then there will be many other epsilon balls that I don't meet, and this will be this ball that I'm looking for. There is some issue with the S1, but it's not a problem. So kind of the main thing you want to do is to cover your set by complex analytic balls. And here there is a completely general complex geometric phenomenon that if you have a complex analytic subset of the unit ball and you want to cover it by epsilon balls, this is how many you will need. And the reason is a kind of completely elementary stuff. So the main ingredient is the, I don't know if I can even call it a theorem, but it's something that appears in the definition of a Lelong number. So it's the claim that if you have a complex analytic set X, which passes through the origin, passes through a 0 in a ball of radius epsilon, then the volume of X intersected with the ball of radius epsilon is greater or equal to some constant times epsilon to the dimension over R of X. Okay, so if a complex analytic set passes through the origin of a ball, you have a lower bound for the volume in the ball. And kind of the lower bound is in fact just the volume of a linear section. So you cannot have, in the real picture, you can have let's say a real curve which passes through some ball, but it's very tiny. It's kind of a little closed circle. And then it passes through a big ball, but it has a very small volume in this ball. But in the complex situation, you can't have it. If you have a complex analytic set, it kind of has to expand in all directions, and you have a lower bound for the volume. So once you get a lower bound for this volume, it's not hard to show that you can cover X by this number of balls. Kind of, you cover it by disjoint balls, and if you had too many balls, then just there will be too much volume. If every ball contains a certain amount of volume, and you know the total volume of the set, it's volume of X, so you can get a bound for how many balls you need. So kind of what all this means is that if I'm working with complex analytic sets, it's enough for me to just know the volume. Okay, if I know the volume, then once epsilon is smaller than this volume, then I can find the ball of radius epsilon, which will be disjoint. Okay, the total number of epsilon balls is like epsilon to the n, but the number of epsilon balls that meet X is only volume X times 1 over epsilon to some smaller number, the dimension of X. Okay, so once epsilon is small enough, I will be able to find an epsilon ball which is disjoint from X. So the only question is how to estimate this. So we need to estimate this. Okay, and I claim that this is where you can use this theorem 1. Okay, because what we have now is a set X. We want to estimate its volume by something like Crofton. I mean, Crofton is in the real case, but in the complex case, there is something called the Alexander Theorem. Alexander. The volume of X is kind of bounded by some constant times the kind of number of intersections and X intersect, I don't know, H for an average plane H. So if you want to compute the volume, you intersect things with linear planes of complementary dimension, you count the number of intersections, and this gives you the volume. Okay, in the real situation, this is called the Crofton formula, and it's also true in the complex situation by Alexander's theorem. So basically, if we want the volume, we just need to compute the number of isolated intersections with some linear things. But all of these intersections, they are just kind of theorem 1 applied to kind of subfoliations, linear subfoliations. Of f. Okay, so if I want to intersect with a given h, this h lives in the xi coordinates. I just choose a kind of a linear subset of this xi vector field, and I look at the foliation that they generate, and then this will kind of theorem 1 will tell me how many intersections I have. So it allows me to estimate this volume. In fact, not just the average volume, just every volume. I'm cheating here a little bit because it could be that when you do this restriction to linear subfoliations, you create new unlikely intersections. So there is some work to avoid this new unlikely intersection. This is actually the most technical part of the paper. But believe me that it can be, by some perturbation arguments, you can get rid of this. So this kind of finishes this reduction of theorem 1, how you get theorem 2 from theorem 1. Now, the more interesting thing is how you get theorem 1 from theorem 2 and why you actually need kind of how theorem 2 comes in. Why do you need theorem 2 when you try to count this kind of intersections between algebraic varieties and leaves? So this is what I want to explain next. Okay, so now I'll show the proof of theorem 2. I'm sorry, of theorem 1. And this will use theorem 2. So there's a base case. I mean, I did theorem 1 using, I proved theorem 2 using theorem 1. So theorem 1 I should prove in the base case without assuming anything. So the base case is n equal to 1. So this is a case that I kind of treated in an older paper a couple of years ago. And here really you don't need these Weierstrass polydisks. But let me show you how it works in n is equal to 1. So n is equal to 1 means instead of foliation, we just have one vector field. We are looking at the trajectory of a vector field. We are restricting a polynomial to this trajectory. And we are asking what is the number of zeros of the polynomial on this trajectory. Okay, that is the question. Okay, so now my algebraic variety should be of codimension 1. It's just given by some polynomial equation. And I want to count the intersections of this with some leaf, which in this case is just a trajectory. So now by let me call it value distribution theory, so something like the Jensen formula or something in the spirit of Nevan Lina theory, you can estimate the number of zeros by looking at the growth of p on the leaf. Okay, so the precise statement I want is the following. I want to say that the number of zeros of p for z in this ball ball in my leaf. This is bounded by the logarithm of the maximum for z in a ball of radius 2 of pz over the maximum for z in a ball of radius 1. Okay, so if you've never seen this theorem, it's kind of surprising. It says that if you want to count the number of zeros of any analytic function, this is only about holomorphic functions. Let's say you have a holomorphic function in a ball of radius 2, and you want to know how many zeros it can have in a ball of radius 1. So it says just take the maximum in the ball of radius 2 divided by the maximum in the ball of radius 1 and take logarithm. Now the intuition should be that a holomorphic function in this context looks like a polynomial. So and the polynomial looks like just a product of its zeros, kind of z minus z alpha for all the zeros. So if you have many zeros, you should look like some big power of z. So you have to have a big growth between, let's say your polynomial looks like z to the n, then it will have maximum 1 on the ball of radius 1, but 2 to the n. By the way, I'm sorry, there should be a constant here, of course. So it's kind of times some constant related with the harmonic structure of this the disk of radius 2 and disk of radius 1. But never mind about this constant. OK, so basically we want to estimate these two things, and then we know how many zeros we have. OK, now I claim that this is very easy to estimate. This is easy. Because basically I have my polynomial, I know its degree, and I know the coefficients. Right? I'm allowed to use the degree of w and the log height of w. So I know the degree, I know the coefficients, and I'm just plugging in points from the leaf, and I'm assuming the leaf is fixed, so it's just a constant. So of course, if you take the maximum of this with this and take log, it will grow polynomially in the degree and the height. So this is very easy. The question is, how do you get this? Because I mean, this you don't want an upper bound, you want a lower bound, and this could be very small. Maybe the polynomial happens to be very small on your leaf. So that is kind of the part where we have to work. OK, so let me show how we get some information on this. So this is what we want. We want lower bound. OK. OK, so where will we get this lower bound? So first I need a claim about this unlikely intersection locus. So I claim that in this case, sigma w, it's equal to the variety given by p, sigma square of p, dot, dot, dot. Okay, this is kind of obvious. So sigma w, it means unlikely intersections. In this case that we have codimension 1, it just means the places where the trajectory is contained in the zeros of p. So for the trajectory to be contained in the zeros of p, it would mean that p and all of its derivatives vanish along the trajectory. So it's exactly this variety defined by all of these polynomials. But I claim that this is also equal to the variety given by p, sigma p, dot, 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 up to sigma to the mu p, where mu is given by, what do I want exactly? Let's say by just a polynomial in the degree of p. We have very precise estimates for it, but it doesn't matter for this case. So I claim that actually you don't need to look at all the derivatives. It's enough to look at the first mu derivatives, where mu is some polynomial in the degree. Okay, so this kind of result is called the multiplicity estimate. So there are many, many multiplicity estimates studied by people from control theory, from transcendental number theory. So there's kind of the best results are due to Nesterenko. And there's another one due to Gabrielov. They are kind of the two of the best, and they are incompatible. So each of them is better in some other direction. And also I have some result that kind of implies both of them, which is based on the idea of Gabrielov. So, but anyway, what we need here is very weak, and either of these would suffice, or much simpler things would suffice as well. So we have this result. OK, so now what else do I need? I need a very simple statement about holomorphic functions, saying that the maximum in the ball of radius 1 of P of z is bounded from below by the maximum of the derivatives at 0, where k goes from 1 up to mu. So basically I'm saying if the function was very small on the ball, then all of the derivatives would have to be small. For example, because of the Cauchy estimates. Okay, so if a function is very small on the entire unit ball, then by Cauchy you get that all of its first derivatives are very small. There is some constant depending on mu, but trust me that this constant is harmless here. Okay, so if we want a lower bound for the function, it's enough to give a lower bound for one of these first derivatives at 0. Okay, and finally, so we just want a lower bound on this. So this means we want to know how small can all of these numbers be. And now this guy is greater or equal with some constant again to the distance between 0 and sigma w. Now this is true because sigma w is the common zero locus of the polynomials. And this kind of result is called the diophantine Loya-Shevich inequality. So this, I mean, for example, this is due to Brownawell. Okay, so these diophantine Loya-Shevich inequalities tell you that if you have a collection of polynomials defined over a number field, then the only reason why they could all be small at some point is if this point is close to their common zero locus. Okay, so the maximum of all of these guys is lower bounded in terms of the distance. Well, distance, I mean, it's a polynomial in distance, I'm sorry, but it doesn't matter here because it goes into log. But this is what the diophantine Loya-Shevich inequality says. Okay, so because all of these polynomials, like C is defined over a number field, P is defined over a number field, these are all polynomials defined over a number field, then the only reason why they could all be so small at the origin is if the origin is actually very close to the common zero locus. And the common zero locus is exactly this sigma w. Okay, so this is how we finished the proof for the one-dimensional case. We got a lower bound for this, we had an upper bound for that, and now we do the difference of the logs and we get the result. So as I said, this strategy I already had several years ago. So I have a paper about the one-dimensional situation, but it seemed very hard to generalize it to several dimensions. Basically because we don't have a good analog of this Jensen formula. So this Jensen formula, or all these results of Nevanlina type theory, they work very well in dimension 1, and they work much less well in higher dimension. So if you have two equations in two variables, it's not clear how to write something like this. If you can just look at their growth, it will not be true. So you need kind of something different in order to count solutions of several equations in several variables. So now I want to show what I do in arbitrary n, and this is where these Weierstrass polydisks come in. OK, so now in arbitrary n, so I have a w which is given by n equations. Let's say p1 up to pn. And then I'll take w tilde where I just drop the last equation. So it will be p1 plus p n minus 1 is equal to 0. And we are looking to count the intersections of w with our leaf. Now this is a set of one codimension lower. So actually, because we have theorem 2, we can find the Weierstrass polydisk for this w tilde. OK, so let me start with finding a Weierstrass polydisk for w tilde. OK, so I have this kind of picture. Well, this it's w tilde intersected with bl. I'm sorry. So I have this kind of picture. Here I have my analytic set. So this set inside here is w tilde intersected with bl. And what we want is to add one extra equation. We have our extra polynomial equation, Pn, and we want the zeros of Pn on this thing that you see here. OK, so here you see actually a curve, because it's w tilde is codimension n minus 1. We intersected with a leaf, we get a curve. We put it inside the Weierstrass polydisk, and now we want to find the zeros of Pn on this curve. OK, is it clear? So we are looking for, we look for zeros of Pn restricted to this w tilde intersect bl. And now I claim that it is very easy to cook up a univariate complex function that will have exactly the same zeros. So it's just like a resultant of two polynomials, except you do it kind of locally for this Weierstrass polydisk. So I define f of z, which is the product. Let's say j goes from 1 to l. L is the number of points in the fiber here, of Pn evaluated at z and wj of z. So let me draw it here. So if this point is z, then I have 3 points. So this will be w1 of z, this will be w2, and this will be w3 of z. OK, so I have these 3 roots. They are moving. So these are not holomorphic functions, w1, w2, and w3. They can have ramification. But when you take this product, then of course it's invariant under monodromy, so there will be no ramification. So this function is just a nice holomorphic function defined on the base here. And the zeros are exactly the zeros of Pn on this curve. So what we want is to count the zeros of this univariate function. And now basically we are back to the context of the previous theorem, except, in the previous theorem we knew how to compute derivatives of this function f. And now this function is kind of built out of several branches of P, and it's more complicated to understand how you will get this bound on the derivatives, so you can apply Cauchy and all this stuff. So this part is a little bit technical. So I will not go into details, but basically we proceed as before, and we replace this ideal kind of xi of p, xi2 of p, dot, 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 by some more complicated differential operators that depend on the foliation. So there are some more complicated differential operators that kind of generalize this sequence of derivatives for several variables. Let's say you have 2 equations in 2 variables. You want to know, do they have an intersection multiplicity of finite order or infinite order? You can kind of express this using some differential operators, which that Dimitri and I studied in some older paper. So we call them multiplicity operators. It's kind of differential operators that control the multiplicity of intersection between a set of equations. So we replace this by what we call multiplicity operators. So these are some kind of algebraic differential operators, not non-linear, but they are quite simple. But just I will not have time to describe this construction. But just trust me that there is some nice notion of differential operators that exactly replaces this. So their common zero locus will be exactly the locus of unlikely intersections. And once you know that one of them is big, then actually you can show that this f should be big. Okay, so there's some technical work there, but I will not go into it. Okay, so this is how we kind of finish the proof. So first we reduce to the one-dimensional case, and then the one-dimensional case, it's basically the same strategy, except we need more work to get the lower bound for f. Now in my remaining 10 minutes, I want to say how this connects to counting rational points. So what is kind of what you get after you develop all of this? So I'll talk about counting, and I'll even say algebraic points instead of rational points. Okay, so let me start with a definition. So let's say I have A in C to the n, just any set. Then I'll denote by A dh. This will be the set of points P in A, such that the degree of P, so I mean kind of the degree of the extension of Q by P, is less than or equal to D, and the height of P is less than or equal to H. So this is, again, logarithmic Weil height. If you don't know what it is, just think about you take the minimal polynomial of this P and take how many bits do you need to write out this polynomial. For example, this is not exactly the logarithmic Weil height, but it will not matter for what I'm saying. Okay, so now I'll state a theorem which is not the most general, but just easy to state. So a theorem: suppose no leaf L contains, we say, a germ of an algebraic curve. So this is kind of an analogous assumption to what Dimitri had. We had to throw out this algebraic part. So now I'm kind of throwing out the algebraic part from all the leaves. I'm saying, let's suppose that there's no algebraic part in any of the leaves. Okay, then the number of points in a ball on the leaf L dh is less than or equal to some polynomial, depending on the foliation, in D and H. Okay, so this is kind of like this Pila-Wilkie theorem, except in the Pila-Wilkie theorem we are looking at the height, not the logarithmic height, and we had the height to the power epsilon. And here, instead of the height, we have just a polynomial in the log of the height. So it's much stronger. This is what is called the Wilkie conjecture, to get kind of a polynomial in the log instead of just h to the power epsilon. And also here we have polynomial dependence on D. So in the regular Pila-Wilkie theorem, we don't have any good control on the dependence on D. The original one was just for rational points. Later it was extended by Pila to any fixed D. But to get it polynomial in D is very useful. In fact, it allows you to get Galois lower bounds by using the Pila-Wilkie theorem. So there is some kind of other reasons why we would want to get this polynomial dependence on D. So here we are able to get it. And well, this is kind of a Wilkie conjecture. For BL. Now, in general, this assumption that the leaf no leaves contain algebraic curves, it's a bit restrictive, but it's not really the correct assumption. Kind of the correct assumption should say that, well, if some leaves contain algebraic curves, then into this estimate you should also put the inverse logarithmic distance to these bad leaves. Okay, and with this full statement, actually, all the diophantine applications go through. So in the diophantine applications, usually you could have something algebraic, but then you know how to control the distance to it, because you have a good description of the algebraic part. Okay, so I will not have time to give really the complete statement of this result, but just trust me that for many of the applications, the full version of this theorem is enough. Now, in my remaining, 5 minutes, I want to just mention some of the original applications that I talked about. So an example of a corollary of this. So corollary, for instance, is that under Oort for modular curves, is decidable in polynomial time. Okay, so under Oort for modular curves means you have a product of modular curves, you have some subvariety of this product of modular curves, and you're looking for CM points. So it means you're looking for points that represent elliptic curves with complex multiplication. And the under Oort conjecture says this set should be finite. I mean, unless your variety contains a special subvariety. So decidable in polynomial time, I mean the set is finite, and actually you can write a computer algorithm that will compute all of these special points. And I mean, this kind of follows from the usual proof of under Oort by Pila, plus the fact that you can completely effectivize the Pila-Wilkie part. Now, I'm kind of hiding some points here under the rug. Let me kind of mention them for you. First of all, I'm saying that it is decidable in polynomial time, but this is an existence result. So I'm saying there exists an algorithm to find all of the CM points. I do not know what is the algorithm. Only there exists an algorithm. And the reason for this is that there is some existential constant. So in the Galois lower bound for CM points, we know that if you have a CM point, then it will have many Galois conjugates, something like some positive power of the discriminant, but with a constant. And this constant, it depends on this. It's called the Ziegel lower bound. It's a very deep lower bound from analytic number theory. And without the Riemann hypothesis, there is some constant there that we don't know how to control. So this constant would come into this algorithm. So we cannot kind of hope by this method really to produce a fully effective result. It's kind of, I'm only saying after you know this constant, you can put it into your algorithm, and then under Oort will be decidable. Now, another small point is that for the real proof of under Oort, you need to work with, not with compact domains. You need to work with the whole modular curve, which is not compact. Okay, it has a cusp. And my result is only about compact things. It's about these finite balls. So there's a few ways to get around this problem. That's why I state kind of I'm writing for modular curves and not for general Shimura varieties. For modular curves, you can kind of get around this problem because there are equidistribution results that tell you that the CM points are equidistributed. So in fact, many of these CM points will land in some compact domain. It's enough to look in a compact domain. But in fact, there are other ways using height inequalities to get over this problem. So I will say almost surely, but let's say probably, you can replace this modular curve by AG. So probably the same is true for just the Shimura variety, the moduli space of Abelian varieties. And this is the most general case when we know that the under Oort holds. It's still not known to hold for Shimura varieties, but probably even in this case, you can get this kind of decidability results. And well, all of the other results that I mentioned by Masser and Zannier and so on, they also become effective using this result, but just I will not have time to give you the details. So I will stop here. Thank you.